Beneath our feet lies a remarkable structure, Earth's crust. This solid outer layer, upon which we live and build our civilizations, is a testament to billions of years of geological processes. The crust may seem unchanging, but it is a dynamic and ever-evolving feature of our planet, shaped by forces deep within Earth's interior. The crust is surprisingly thin compared to the other layers that make up our planet. It varies in thickness, being thicker under continents and thinner beneath the oceans. But despite its relatively small size, the crust plays a crucial role in supporting life on Earth. It provides the solid ground upon which we stand, the soil in which our food grows, and the landscapes that shape our world. Imagine a young Earth, still in its infancy, a time when our planet was just beginning to take shape. It was a fiery sphere of molten rock and metal, a chaotic and violent environment. This was our planet billions of years ago, a time before continents, oceans, or even an atmosphere as we know it today. The surface was barren and inhospitable. The intense heat, generated by the gravitational collapse of materials that formed Earth, kept the planet in a molten state, preventing any solid land from forming. Instead, it began to differentiate, with denser materials like iron and nickel sinking towards the center, creating a layered structure. This process, known as differentiation, led to the formation of Earth's core, a dense metallic sphere at the heart of our planet, composed primarily of iron and nickel. Lighter materials like silicates rose towards the surface, forming a vast molten ocean of magma that covered the planet. As Earth continued to cool over millions of years, the outer layers of this magma ocean began to solidify, forming a thin, fragile crust. This marked a pivotal moment in Earth's history, the birth of the planet's first crust, a solid surface that would eventually support life. As the early Earth continued to radiate heat into space, the outermost layer of the magma ocean began to cool. This cooling process was gradual, taking millions of years, and as temperatures dropped, a remarkable transformation began to occur: crystallization. Within the molten rock, minerals began to crystallize as they cooled below their melting points. These tiny crystals, suspended in the remaining magma, marked the first solid materials to form on Earth's surface. Over time, these crystals accumulated, forming a thin, fragile crust atop the still molten interior. This early crust was far from the stable continents we know today. It was constantly being broken and reformed by volcanic eruptions, meteorite impacts, and the churning of the molten magma beneath. Volcanoes played a pivotal role in shaping Earth's early crust, acting as both creators and destroyers of the landscape. Driven by the intense heat within the planet's interior, these fiery mountains erupted with tremendous force, spewing molten rock, gases, and ash onto the surface. The sheer power of these eruptions was unimaginable, transforming the surface in dramatic ways. These eruptions, far more frequent and powerful than any we see today, had a profound impact on the primitive crust. The relentless volcanic activity was a constant force of change, molding the young Earth's surface. They ripped apart existing crustal fragments, adding new material to the surface and constantly reshaping the landscape. This process of destruction and creation was essential in forming the diverse geological features we observe today. Volcanic gases released into the atmosphere contributed to the formation of Earth's early atmosphere, a crucial step in the development of our planet. These gases included water vapor, carbon dioxide, and other elements that would later support life. Volcanic activity also played a crucial role in the formation of some of Earth's oldest rocks. These ancient rocks provide a window into the planet's formative years, offering clues about the early conditions on Earth. As molten rock, known as magma, rose from the mantle and erupted onto the surface, it cooled and solidified, forming igneous rocks. These rocks are the building blocks of the Earth's crust, and their formation marked a significant step in the planet's geological evolution. Section 5. Ancient Witnesses, the Oldest Rocks and Minerals. To unravel the mysteries of Earth's early crust, scientists turn to ancient witnesses, the oldest rocks and minerals found on our planet. Some of the oldest known rocks on Earth are called zircons, tiny mineral grains that have survived the relentless forces of erosion and geological upheaval for billions of years. These remarkable minerals, some dating back over 4 billion years, tell a fascinating story about the early Earth. By analyzing these inclusions, scientists can determine the age of the zircon and gain insights into the chemical composition of the magma from which it crystallized. These ancient zircons have revealed that Earth's early crust was surprisingly similar in composition to the continental crust we see today. Section 6. Two types of crust, continental and oceanic divide. As Earth's crust continued to evolve, a fundamental distinction emerged: the formation of two distinct types of crust, continental and oceanic. Continental crust, as its name suggests, forms the continents, the large land masses that rise above sea level. It is thicker, less dense, and composed primarily of granite, a light-colored igneous rock rich in silica and aluminum. Oceanic crust, on the other hand, forms the floor of Earth's oceans. It is thinner, denser, and composed primarily of basalt, a dark-colored igneous rock rich in iron and magnesium. The differentiation of Earth's crust into these two distinct types was a pivotal event in our planet's history. Section 7. A dynamic surface plate tectonics takes the stage. The formation of continental and oceanic crust was just the beginning of Earth's dynamic journey. As the planet continued to cool, the crust, once a continuous shell, broke into a series of massive plates. These plates, floating on the semi-molten mantle beneath, are in constant motion, driven by convection currents deep within Earth's interior. This dynamic process, known as plate tectonics, has shaped our planet for billions of years. The interactions between these moving plates are responsible for some of Earth's most dramatic geological features, from towering mountain ranges to deep ocean trenches. At mid-ocean ridges where plates move apart, magma rises from the mantle to create new oceanic crust. Section 8. Recycling and renewal. The crust in constant motion. Plate tectonics is not just about creation and destruction, it's also a remarkable recycling system. As oceanic crust is subducted back into the mantle, it carries with it sediments and water, which can melt and rise back to the surface through volcanic eruptions. This constant recycling of Earth's materials has played a crucial role in shaping the planet's geology, atmosphere, and oceans. The continuous movement of tectonic plates ensures that Earth's crust is in a constant state of flux. Continents drift across the globe, colliding and breaking apart over millions of years. Oceans open and close, their floors constantly being renewed. Section 9. A window to the past, unraveling Earth's history. The rocks that make up Earth's crust are like pages in a history book, preserving clues about the planet's long and dynamic past. By studying these rocks, their composition, age, and the fossils they contain, scientists can piece together the story of Earth's evolution. Geologists use a variety of techniques to unravel Earth's history. Radiometric dating allows them to determine the age of rocks by measuring the decay of radioactive isotopes. Paleomagnetism, the study of Earth's ancient magnetic field, provides clues about the past locations of continents, and the analysis of fossils, the preserved remains of ancient life, reveals the evolution of life on Earth. Each discovery adds a new layer of understanding to the story of our planet. Section 10. The ever-evolving crust. A story still unfolding. The formation of Earth's crust is not a story confined to the distant past. It's a process that continues to this day. Every year, new crust is generated at mid-ocean ridges, while old crust is recycled back into the mantle at subduction zones. Continents continue to drift, albeit slowly, reshaping the face of our planet. The forces that shaped Earth's crust billions of years ago are still active today, albeit at a slower pace. Understanding the processes that shape Earth's crust is essential for comprehending the planet we live on. Section 11. Conclusion. A planet shaped by time and transformation. The birth of Earth's crust is a testament to the immense power of geological processes operating over vast stretches of time. These processes have sculpted the very surface we walk on, creating a dynamic and ever-changing landscape. From a fiery, molten beginning to the solid foundation we stand on today, the crust has undergone a remarkable transformation, shaped by the relentless forces of plate tectonics, volcanic activity, and erosion. Each of these forces has played a crucial role in molding the Earth's surface. This journey through billions of years has left an indelible mark on our planet, creating the continents, oceans, and mountains that define our world. The evidence of this incredible journey is etched into the very rocks and landscapes that surround us. The crust, once a thin and unstable skin, has become the bedrock of life, providing the solid ground upon which ecosystems flourish and civilizations rise. It is the foundation upon which all terrestrial life depends. The story of Earth's crust is not just a tale of the past, it's a story still unfolding, a story that continues to shape our present and our future. As we look to the future, we must remember that the forces that shaped our world are still at work, constantly reshaping the planet we call home.